This video is created for educational and informational purposes only. It uses AI-generated visuals and animations to illustrate publicly available scientific and technical information about the uranium enrichment process used in civilian nuclear power. We do not provide instructions for any prohibited activities, and all content complies with YouTube policies. Nuclear facilities are highly regulated, secure sites operated under strict international and national safety standards. Welcome to the NextGen Process channel, where we explore the inner workings of the world's most advanced and carefully regulated industrial facilities using clear, detailed explanations and stunning AI-generated visuals. Today, we are taking a deep, comprehensive journey inside a uranium enrichment plant to understand exactly what happens in one of the most technically sophisticated processes behind modern nuclear energy. The title of this video asks about the entire dangerous process behind nuclear energy. But let me be crystal clear from the start. This is not about weapons or military applications. Our focus is strictly on the civilian nuclear fuel cycle that powers commercial nuclear reactors and generates clean, low-carbon electricity for millions of homes and businesses around the world. The process is highly regulated, requires billions of dollars in investment, and operates under the strictest international oversight to ensure safety and peaceful use only. Uranium is a naturally occurring radioactive element found in small amounts throughout the Earth's crust. In its raw form, it consists of two main isotopes, uranium-238, which makes up roughly 99.3% of natural uranium, and uranium-235, which accounts for only about 0.7%. The critical difference lies in their atomic structure. Uranium-235 is fissile, meaning its nucleus can split apart when struck by a neutron, releasing enormous amounts of energy in the form of heat. This controlled chain reaction is what ultimately produces the steam that drives turbines and generates electricity in nuclear power plants. Uranium-238, on the other hand, is fertile but not fissile under normal reactor conditions. For most commercial light water reactors used today, the concentration of uranium-235 needs to be increased from 0.7% to between 3 and 5%. Some advanced reactor designs may require slightly higher levels, but still far below the 20% threshold considered highly enriched uranium and well below the 90% needed for weapons. Achieving this tiny but crucial increase in concentration is extraordinarily difficult because the two isotopes are chemically identical and differ only by a small difference in mass. Uranium-238 is just 1.3% heavier. This is why enrichment plants are among the most energy-intensive and precision-engineered facilities ever built. Throughout history, the development of uranium enrichment has been tied to both energy production and national security concerns. But today, the vast majority of enrichment capacity worldwide is dedicated to peaceful civilian power generation. Countries like the United States, France, Russia, China, and others operate these plants under rigorous safeguards from the International Atomic Energy Agency, or IAEA. In this video, we will walk through every major stage of the process with scientific accuracy, emphasizing the engineering marvels, the safety protocols, and the role this technology plays in fighting climate change by providing reliable baseload electricity without direct carbon emissions. Let's begin our detailed exploration. The journey starts far from the enrichment plant, deep in the Earth's crust, where uranium ore is mined. Uranium deposits are found in several countries, with major producers including Kazakhstan, Canada, Australia, Namibia, and the United States. Mining can be done through open pit operations for shallower deposits or underground shafts for deeper ones. In some cases, in situ recovery, also known as solution mining, is used where a leaching solution is pumped underground to dissolve the uranium without removing large amounts of rock. Once the ore is extracted, it is transported to a milling facility located nearby to minimize handling of radioactive material. At the mill, the ore is crushed into a fine powder and then chemically leached using sulfuric acid or alkaline solutions to dissolve the uranium. The resulting slurry undergoes a series of purification steps, including precipitation, solvent extraction, and drying, to produce a concentrated powder known as yellow cake. Yellow cake is primarily triuranium octoxide, or U3O8, and despite its name, it looks more like a bright yellow or greenish powder. At this stage, the material is still natural uranium with the original 0.7% U-235 concentration. No enrichment has occurred yet. Yellow cake is packed into sturdy 5.5-gallon drums and shipped under strict transportation regulations to a conversion facility. The entire mining and milling process is carefully monitored for radiation levels, worker exposure, and environmental impact. Modern mines and mills operate with advanced ventilation systems, water treatment plants, and reclamation plans to restore the land after operations end. It is important to note that the radioactivity of natural uranium ore is relatively low compared to spent nuclear fuel, but safety protocols are still rigorous because prolonged exposure must be avoided. This stage sets the foundation for the entire fuel cycle. Without high-quality yellow cake, the subsequent chemical conversions and enrichment would be impossible. Interestingly, the global supply of uranium is managed through long-term contracts between mining companies and utilities, ensuring a stable supply for the hundreds of nuclear reactors operating worldwide. As of recent years, annual world uranium production hovers around 50,000 to 60,000 tons, with demand driven by the growing interest in nuclear power as a clean energy source. Now that we have our starting material, let's move on to the critical conversion step that prepares uranium for enrichment. Yellow cake cannot be enriched in its solid oxide form. The next essential stage is conversion, where it is chemically transformed into uranium hexafluoride, commonly known as UF6. UF6 is unique because it can be converted into a gas at relatively low temperatures, making it suitable for the enrichment technologies used today. The conversion process begins at specialized facilities equipped with corrosion-resistant materials because many of the chemicals involved are highly reactive. First, yellow cake is purified further and reacted with hydrofluoric acid to produce uranium tetrafluoride, or UF4, often called green salt because of its color. This intermediate is then fluorinated again using elemental fluorine gas to create UF6. The entire sequence involves multiple high-temperature reactions carried out in sealed vessels under carefully controlled conditions. Once produced, UF6 is a white crystalline solid at room temperature. However, when gently heated to about 56 degrees Celsius, roughly 133 degrees Fahrenheit, it sublimes directly into a gas without melting. This gaseous form is the feedstock that will enter the enrichment plant. The conversion facilities are designed with multiple containment layers, leak detection systems, and emergency scrubbers to neutralize any accidental releases, since UF6 reacts violently with moisture in the air to form hydrofluoric acid and uranyl fluoride. Workers at these plants wear specialized protective gear, and the facilities operate under licenses from national nuclear regulatory bodies such as the U.S. Nuclear Regulatory Commission or equivalent agencies elsewhere. The output UF6 is loaded into large, robust steel cylinders that are pressure tested and inspected before being transported to the enrichment site. Each cylinder can hold several tons of material and is designed to withstand extreme conditions during shipping. This conversion step is often overlooked in popular discussions, yet it is a vital bridge between raw mining output and the precision engineering of enrichment. Without it, the separation of isotopes would be impossible using current commercial methods. With our UF6 gas ready, we now enter the most technologically impressive part of the entire process, the enrichment plant itself. Modern commercial uranium enrichment is dominated by the gas centrifuge method, which has replaced the older and far more energy-hungry gaseous diffusion process used in the mid-20th century. The gas centrifuge is a masterpiece of precision mechanical engineering. Each centrifuge consists of a tall, slender rotor tube made from high-strength materials such as carbon fiber or maraging steel, spinning inside a vacuum-sealed casing. When UF6 gas is fed into the rotor, the cylinder spins at incredible speeds, typically between 50,000 and 70,000 revolutions per minute. with the outer wall reaching velocities of several hundred meters per second. This generates a centrifugal force hundreds of thousands of times stronger than gravity. Because of this force, the slightly heavier UF6 molecules containing U-238 are pushed outward toward the rotor wall, while the lighter molecules containing U-235 concentrate closer to the central axis. A small temperature gradient is often applied along the length of the rotor to create a countercurrent flow. This flow moves the enriched gas higher in U-235 toward one end of the centrifuge, and the depleted gas, called tails, higher in U-238 toward the other end. Special scoops or pipes then extract these two separate streams. The separation achieved in a single centrifuge is very small, only a tiny fraction of a percent, which is why thousands of machines must work together in a cascade. The rotors must be perfectly balanced to prevent vibration that could cause catastrophic failure. Engineers use advanced materials and computer-controlled manufacturing to achieve the necessary precision. Each centrifuge is individually monitored, and the entire hall is kept under strict environmental controls, precise temperature, humidity, and pressure to maintain optimal performance and safety. The vacuum inside the casing reduces friction, allowing the rotors to spin continuously for years with minimal energy input compared to older technologies. This method is so efficient that a single modern centrifuge plant can supply fuel for multiple large nuclear reactors while using only a fraction of the electricity required by gaseous diffusion plants. The technology itself cannot produce a nuclear explosion because the enrichment levels for power reactors are kept low. The danger here is managed through engineering, chemical toxicity of UF6, the high-speed rotating machinery, and the need to prevent any unauthorized diversion of material. To achieve the required 3 to 5% enrichment, individual centrifuges are arranged in a massive cascade system, a carefully engineered network of thousands of machines connected in series and parallel stages. The slightly enriched output from the first stage becomes the feed for the second stage, and so on, while the depleted tails are recycled back to earlier stages for further extraction. This cascading continues through dozens of stages until the product stream reaches the target enrichment level. A typical commercial enrichment plant may contain 10,000 to 50,000 or more centrifuges housed in large, secure halls. The plant is divided into secure zones with controlled access, radiation monitoring, and material accountancy systems that track every gram of uranium entering and leaving the facility. Advanced computer control rooms allow operators to monitor thousands of parameters in real time, using artificial intelligence to optimize flows and detect even the smallest anomalies. The layout is designed for both efficiency and safety. Feed, product, and tails lines are kept separate. UF6 is handled in gaseous or solid form within sealed piping systems. The entire facility is surrounded by physical security barriers, surveillance and response teams to meet international standards. Power is supplied through redundant sources, often including on-site backup generators. Because any interruption could affect the delicate balance of the cascades, modern plants are also incorporating more sustainable practices, such as improved energy recovery and reduced water usage. The scale is enormous. A single large facility can produce enough enriched uranium to fuel dozens of gigawatts of nuclear capacity, enough to power millions of households with clean electricity year-round. The engineering required to keep tens of thousands of high-speed rotors running continuously 24 hours a day, 365 days a year, represents one of the highest achievements in industrial precision. Once inside the cascade, the UF6 gas flows continuously. At each stage, small amounts of enriched and depleted material are withdrawn and sent to the next appropriate level. The product stream, now enriched UF6, is collected and periodically sampled for precise assay to confirm the exact percentage of U-235. Quality control is relentless. Any deviation can affect reactor performance or safety margins. Throughout the plant, thousands of sensors monitor pressure, temperature, flow rates, and vibration. AI-driven systems analyze data patterns to predict maintenance needs before problems arise. If a centrifuge shows signs of imbalance, it can be isolated automatically without shutting down the entire cascade. Defective machines are removed and replaced during scheduled outages, with the rotors being carefully dismantled in shielded areas. The depleted tails, which contain mostly U-238, are stored in cylinders for potential future use or further processing. In some cases, depleted uranium is used in industrial applications such as radiation shielding or as counterweights after it is converted out of the fluoride form. Nothing is wasted unnecessarily, though all radioactive materials are managed under long-term storage and regulatory oversight. This level of monitoring and control ensures that the process remains safe, efficient, and compliant with every international non-proliferation agreement. The operators are highly trained engineers and technicians who undergo continuous certification and background checks. After enrichment, the UF6 gas is transported to another conversion facility where it is chemically transformed back into uranium dioxide powder, UO2. This involves hydrolysis and reduction reactions carried out in controlled environments. The UO2 powder is then pressed into small ceramic pellets about the size of a fingertip, sintered at high temperatures to achieve high density and strength, and loaded into thin metal tubes called fuel rods. These rods are typically made of zirconium alloy, chosen for its low neutron absorption and corrosion resistance. Dozens or hundreds of fuel rods are then bundled together into fuel assemblies, large, rectangular, or square structures that will eventually be placed inside the reactor core. Each assembly is carefully inspected, tested for dimensional accuracy, and cleaned before being shipped to the power plant under armed escort and heavy security. A single fuel pellet can produce as much energy as a ton of coal or hundreds of gallons of oil, highlighting the incredible energy density of nuclear fuel. The entire post-enrichment process ensures that the fuel is ready for safe, controlled fission inside the reactor. Safety is the absolute top priority at every enrichment plant. Multiple redundant containment systems, emergency shutdown capabilities, and rigorous maintenance schedules prevent accidents. UF6 is chemically toxic rather than highly radioactive at this stage, so protocols focus on preventing leaks and protecting workers from inhalation or skin contact. Radiation doses are kept far below regulatory limits through shielding, distance, and time controls. International safeguards administered by the IAEA include cameras, seals, and material accountancy that ensure no material is diverted. National regulators conduct frequent inspections. The technology itself is designed so that commercial enrichment levels cannot lead to a nuclear explosion. The real risks are industrial in nature: high-speed machinery, corrosive chemicals, and the need for strict proliferation controls. And these are managed through world-class engineering and oversight. Uranium enrichment is the gateway to nuclear power, which currently provides about 10% of global electricity and over 20% in the United States, with even higher shares in countries like France. As the world seeks to decarbonize, many nations are expanding nuclear capacity, driving demand for new enrichment facilities. Innovations such as advanced centrifuges and research into laser enrichment promise even greater efficiency and smaller footprints. From the early days of the Manhattan Project through today's commercial plants, the technology has evolved dramatically while maintaining a strong commitment to peaceful use. The future of enrichment is tied to advanced reactors, small modular designs, and a global push for clean, reliable energy. We have now covered the entire journey inside a uranium enrichment plant. From the science of isotopes to mining, conversion, the breathtaking precision of gas centrifuges, the massive cascade systems, post-enrichment fuel fabrication, and the rigorous safety and regulatory frameworks that keep everything secure and peaceful. It is a testament to human ingenuity that we can harness the power of the atom for clean electricity while managing every risk with extraordinary care. If you found this detailed educational exploration valuable, please give the video a thumbs up and share it with others who want to understand how our energy systems truly work. And if you're not already part of the community, join the NextGen Process family right now by subscribing to the channel and turning on the notification bell. We release new in-depth factory tours, industrial process breakdowns, and behind-the-scenes looks at cutting-edge technology every single week, so you'll never miss an episode. Drop a comment below What other energy or industrial process would you like us to explore next? Perhaps nuclear fuel fabrication in even greater detail, a modern gigafactory, or the inner workings of a fusion research facility? Thank you so much for watching. Stay curious, stay informed, and we'll see you in the next video.